Hello everyone. I would like to talk about a few of the key ideas that are pretty important for the SMO Senior. The SMO Senior is sort of in between the SMO Junior and SMO Open in difficulty, but in my opinion, it's actually the easiest of the three to prepare for. Now, I say it's the easiest to prepare for, that's not the same thing as the easiest. But why it's easy to prepare for is that 90% of it is going to be just on algebra. And if 90% of it is on algebra, then at least we know what we are getting into. So let's try to get comfortable with some of the important algebraic ideas in the SMO Senior. The first thing is a slight exaggeration, but it is generally true that you should consider the possibility that everything's a quadratic. Everything's a quadratic includes, well, literal quadratics, right? So if you have a literal quadratic, we know that we have lots of tools to deal with quadratics. For instance, if you're told that a quadratic has no real solution, then one of the things we can do is to use the discriminant. So your discriminant has to be less than 0. And so P is going to be less than negative 25. Now, I'm not always going to go through everything in so great detail. The plan is that we're going to look at maybe one example or two examples in more detail for each theme. And then we're just going to look at some other examples where hopefully you can see how things are quite similar. Or can you? Well, this is a slightly more disguised quadratic, but only slightly. I hope that you are able to see that log 2x is repeated. Log 2 log 3y is also repeated. And so really, what we have gotten ourselves is just a quadratic in these two variables. If you can see it, then great. If you cannot see it, then just call these things A and B. As I mentioned in the junior video, it's often a good idea that if you can't find something, but it keeps on appearing and you are getting confused by how complicated it looks, just to get rid of it by calling it A and B. At this point, I'm sure you can see that this is just going to be a very simple equation to solve. And I'm going to leave the details to you because we will talk about logarithms in a little while. This is a quadratic in logarithms. And this is a quadratic. Well, it's two quadratics, isn't it? It's a quadratic at the top and bottom in tangent x. We are also going to talk about trigonometry later, but I want to keep on emphasizing on this theme first. Everything's a quadratic. This here is not a question on trigonometry. Well, maybe just one iota of trigonometry. You need to know that tangent from minus 90 degrees to 90 degrees is just going to take on all real numbers. And so therefore, if tangent x can be any real number, then I should just get rid of it and let it be, say, z. At this juncture, we no longer have any trigonometry in the question because tangent x can be anything. So why not just replace anything by something else, like z? The question is effectively asking you to find the maximum value of y, right? And then after that, adjust it to make it a positive integer. You want to get the maximum value of y from here. The easiest way is a quadratic, so multiply it over write it as a quadratic in Z, where, of course, you're meant to treat it as y is just a coefficient. And then after that, you want to make sure that for your choice of y, z must exist. So your discriminant has to be greater than or equals to 0. And once again, I'll leave you to work out the details of this, but you're going to find that it's not that hard to calculate square root 33y minus 5 at the optimal value of y. It will turn out to be a nice value. Now, this is often how these things go. There are many ways to disguise a quadratic, and when there are so many ways to disguise a quadratic, you have to take a quadratic or something related to a quadratic as your goal. Don't run away from a quadratic, run towards a quadratic. It's kind of like a fire extinguisher. Now, none of us would love to use a fire extinguisher because that means there is a fire. But you would much rather have a fire extinguisher than not to have one. So quadratics are the extinguishers for all these weird equations. If you can view it as a quadratic, we have lots of tools to help us. Now, even in an example like this one here, there is something to do with a quadratic, along with a small dose of wishful thinking. You do realize that in this equation here, we have got 3 unknowns and only one equation. The problem doesn't say x, y, z are integers, and so we would expect that normally something like this has many possibilities, unless there is something very unusual going on. I can see that the square and the absolute value and the square root don't really mix. These are 3 different types. It's like oil and water. Or if you are doing Sec 3 or Sec 4 chemistry, it's like a polar and non-polar substance. So you are trying to deal with them. You can't mix them, so you have to deal with them individually. And I don't really have much else to say except for the middle guy is the one that is most susceptible to being simplified, right? You can't do anything with the other two. They are already quite nice. This one's the ugly one. Now I'm going to say that this is a quadratic, which sounds a little bit strange because you might say, no, it's not a quadratic, it's a bunch of square roots. Well, remember that a quadratic, first of all, there's a quadratic equation versus a quadratic expression. Here I'm saying this is an expression, and also a quadratic in terms of can be tangent, it can be logs, or it can be a quadratic in terms of a square root. To help us see that, we can let a be square root x minus 11 and complete our substitution by letting x be a squared plus 11. Perhaps you can already see what's happening. This is just a plus 7. It cannot be negative of a plus 7 since a is positive. Do you see what has happened here? Now we are left with 3x minus y squared plus a plus this absolute value equals to 7. Sorry, the 7 cancels out, isn't it? So it's 0. That's what we want. Because all of these cannot be negative. So everything must be equal to 0. And from here, it's easy to solve. I hope you see the progression, right? When we were doing the SMO Junior, linear equations are sort of like taken as assumed, but quadratics are seen as a little bit more challenging. If we have to complete the square, if we have to use some expansions, if we have to use a quadratic formula, that's taken as complicated. For the SMO Senior, that's taken to be a baseline. You shouldn't find it to be scary. You should find it as the moment I can simplify something into a quadratic or thereabouts, I have succeeded. I promised that we'll talk about logarithms and trigo, so let's talk about logarithms now. And I want to start with something that I always like to share, which is that, do you know that the word logarithm actually is a word that tells you what it does? Now, the word logarithm in Greek comes from two words, logos and arithm. Now, arithm, of course, you can guess that is where you get the word arithmetic in English. So it basically means calculations. Logos is something that your English teacher or your philosophy teacher or your literature teacher would have been telling you about. Logos usually means logic, but it can also mean a few things, right? Greek words tend to have a few different meanings. So logos can mean logic, it can mean reason, and it can mean comparison. Now, in this case, logos is used in the comparison sense in the word logarithm, and by comparison, the specific comparison that it is referring to is ratios. Logos is referring to ratio, so the word logarithm is just calculations using ratios. Now, why is that the name logarithm? Because of our change of base formula, right? We know that if we have log base a of b, that is just going to be log base n of b over log base n of a. Is that not a ratio? So every logarithm is just a ratio of logarithms. I don't know if that sounds very impressive, but it's going to do a lot, as we shall see. For this first example, this is not very hard to do directly, but just to show you what we can do, we can just write this as a ratio, and likewise for the other two. Now notice that I didn't even prepare a base. Technically it means it's base 10, but it's more that I don't care what base it is, it's just temporary to emphasize the fact that we are looking at ratios. So when you multiply them, you get log 2018 over log 2021, which you can move back in again like this. So logarithms are just ratios now. The answer in this case is obviously 2018. This is a very dramatic form of ratios because from what you've just seen, it effectively means that you can quote-unquote cancel things out in that way. That's a luxury that we don't always have, but it's still an idea that we usually take away. For instance, in this question here, we are again going to just use our change of base. Now, what you want to do is to pick a good base. And from what I can see here, I don't know what's a good base. Because all the options are 2 and 3, and maybe you see, maybe you don't see why they are 2 and 3. So what I can do is just don't pick a base if I'm not sure. Now, of course, you need to know basic identities to solve a question. I know we always say that Olympiads are all about problem solving and about creativity, and that is absolutely true. But you still need basic tools. It's like trying to play badminton without a shuttlecock or without a racket. It just can't be done, right? You still need it. You don't need the most expensive shuttlecock, you don't need competition grade rackets, but you need a racket and a shuttlecock. So you need your basic logarithm identities, and the basic logarithm identity we need here is our power rule. because 9 and 25 are 3 squared and 5 squared, 3 cubed and 5 cubed. Probably you noticed that already from the very start. That means that we effectively can take that out and cancel them out again, which means that all of them are going to just be log 3 over log 5, log 3 over log 5, and log 3 over log 5 again. So this cancels. And log 8 is 2 cubed, so that's also 3 log 2. So you get log base 2 of 3. And more generally speaking, what we have just said is that log of a power with a power, you can cancel off the power and just take the simpler result. So all these three things here in the brackets turned out to be the same because of this more general property. So logarithms are just ratios. You can cancel common things, but the things are a little bit different from what we're used to for fractions. If you see a question like this, it doesn't change anything. Understand that based on what we are given here, it means x is just a ratio again. And log base 21 of 3, after you split it like this, 21 is 3 times 7. So that's x. Now what you want is log 9 over log 7, and 9 is 3 squared, so 2 log 3 over log 7. So effectively, you just need to get from here to here, and you know that it can't possibly matter what log 3 and log 7 are. So if you want to even just treat it as a plus b is log 3 plus log 7, and then a over a plus b is x, find 2 times of a over b in terms of x. This is all well and good. Right? It can't be important enough that they are log 3 and log 7 because those two quantities are barely related to each other at all. So how you would do this is just in a couple of steps. First of all, flip it over. Second of all, a over a is 1. So take it out. And second of all, flip it back again. And that will end up with your 2a over b. Notice that what I've done is draw a bunch of arrows. This is how you want to think about a lot of your calculations and your relationships when you're doing algebraic stuff, which I'm going to get to in a little while. But first, a short detour to talk about polynomials, and we begin by returning back to quadratics once more. I think we need to know that there is one more thing about quadratics which we are a bit less often taught, especially if you are not as familiar with Olympiads, which is our Vieta's formulas. So Vieta's formulas is one relationship that tells you about the roots of polynomials, and we'll start with quadratics. If let's say that I take a generic quadratic and I call the roots p and q. Now Vieta's formulas tells you that p plus q is negative b over a and pq is c over a. The reason is very simple. Ax squared plus bx plus c, if the roots are p and q, can be factorized as x minus p, x minus q times the leading coefficient a. And if you compare coefficients, straight away you're going to get PQ is C over A and P plus Q is minus B over A. Pro tip, if you suddenly forget the order of it, try something simple like x squared minus 3x plus 2 is x minus 1, x minus 2. Straight away, you will see that 1 times 2 is the thing behind, 1 plus 2 is the thing in the middle. So you do not get confused in the order of B and C. Now let's apply it to this problem. So Vieta's formulas, or sometimes it's called Vieta's equations, the sum of the roots is m plus n, product of roots is mn, and A is 1, B is negative 7m, and C is 5n. So A is 1 allows us to very easily write in 7m and 5n. Which means that this is not really very much of a mystery at all. Since n is non-zero, this just means m is 5, and then n is 30. Now find a quadratic equation whose roots are m over n and n over m. We already know that. M over n and n over m are 6 and 1 over 6. So 6 and 1 over 6, if we use Vieta's formulas the other way, it would mean that your sum is 37 over 6 and your product is 1. So you would need to make sure that minus b over a and c over a are these two values. You can always set a to be 1, which would give you minus b is 37 over 6 and c is 1. So this would be your equation. It doesn't match up with anything, so we can just multiply it by a constant that does not change our roots. We have seen enough of quadratics, so we do not always need to stop at quadratics. We can also look at cubic stuff. For cubics, and we don't need to stop at cubics, but if you understand how cubics work, no reason why you can't figure out, let's say, a quartic or higher by yourself. But rest assured the SMO is not going to waste your time on, let's say, a degree 7 Vieta's formulas. Now, let's say that this is our cubic equation. And your roots are PQR. I'm going to derive it again, just like what we have done for the quadratics. I can't even say what the formula is because I don't know what the formula is going to tell me. So I shall just manually do what we did earlier and see the outcome. So factorize it and divide by a. And then I'm going to expand the right hand side of this. So you start with x cubed. What's the x squared coefficient? The x squared coefficient would be x times minus r, x times minus q, x times minus p. So minus p plus q plus r, x squared. Next, what's the x coefficient? It means that you took negative p and negative q, or negative p and negative r. Multiplying them together, you get plus all these combinations. And finally, if you don't take x at all, you get minus pqr. So, what's the implication? If we compare coefficients, p plus q plus r is minus b over a, pq plus pr plus qr is c over a, and pqr is minus d over a. So if you want to try remembering this, what I would suggest is to do this. Right? First of all, remember that the sum of roots is always minus b over a, in the sense that a is your leading coefficient and b is your next highest coefficient. For the rest of it, you just proceed down b, c, d, e, and so on, and you alternate between minus, plus, and so on. Whereas for the left side, what you're doing is that you just take one at a time and add them, two at a time and add them, or three at a time and add them, and if you have more than three, this can go on a little bit longer. Alright, so let's see how it would look like in our question. But don't get too attached to the letters, because as you can see here, the names of the roots are a, b, and c, which is a bit confusing if we are thinking, oh, a plus b plus c is minus b over a. Well, remember the a, b, and c are not just letters. A, b, c are playing the roles of roots in the question, but they were playing the roles of coefficients in what we just wrote down. So don't get mixed up. So Vieta tells you here that a plus b plus c is minus negative 35 over 3. The next one, ab plus ac plus bc is equal to what? Oh, there's no x term here, so that just means that the x coefficient is 0. So that's nice. And finally, abc is negative 500 over 3. Now from here, things are relatively straightforward, because all you need to do is to just add these fractions together. And I'll leave you to work out the algebra from these three equations in order to get what should be quite a nice answer. So you've seen that we can use Vieta's formulas or Vieta's equations to solve some of these questions where they tell you about the roots. But just one more thing that we can handle is when, wait, the question doesn't say anything about roots here. Have we gone off track? Not really. Remember, we started off by saying everything's a quadratic. Now, I'm not saying this is a quadratic, but for polynomials, everything is all about the roots. Because think about it. If you know all the roots of a polynomial, you more or less know exactly what the polynomial is. If I told you that the roots of a polynomial are 1, 2, and 3, and it's a cubic, then I already know that the polynomial looks like x minus 1, x minus 2, x minus 3. That's how you get roots 1, 2, and 3. And technically what I've just invoked is the factor theorem. But it's common sense, right? It is x minus 1, x minus 2, x minus 3. Yeah, and I should add times a constant, possibly. So as long as you know the roots of a polynomial, you basically know what it is. We've seen that for quadratics, we have seen that for a cubic. Now let's look at this example here. And what I want to do is to try to rephrase the given condition into something about roots. So let me shift this over. Can I say that 1 to 5 are roots of Pn minus 120 over n? Not quite. Why? Because that's not a polynomial. So it's not wrong, but it's not quite what we want. To make this a polynomial, I have just a very simple proposition. Let's multiply by n. And so the conclusion is that the polynomial xpx minus 120 has roots 1, 2, 3, 4, 5. And like what we have seen here, xpx minus 120 must therefore be x minus 1, x minus 2, x minus 3, x minus 4, x minus 5, and potentially a constant. How do we know whether that is a constant? or for that matter, what is the constant? Well, usually we will substitute in one special value to check. And the special value, more often than not, will be 0. It doesn't have to be 0, but it's just whatever would allow you to not know the polynomial px. Here, if I put x is 0, then I don't need to know what p of 0 is. Well, we are fortunate enough that in this case c is actually 1. So there was no constant. And so to find p of 6, just let x equals to 6. So p of 6 will be 40. You might be asking, why wouldn't it just be 120 divided by 6? Well, the simple answer is that it just isn't. Why does it have to be? Right? There are lots of patterns that just work for a while and then stop working. And p is a polynomial. P is not supposed to be a rational function. So it can't actually be that p is 120 over n everywhere, otherwise that's not a polynomial at all. So you would expect that the pattern will stop at some point. It's not that shocking that your next answer is not going to just be 20, even though it is certainly a very tempting proposition. So we're at a halfway point, and I have done my best to hold this off for a while, but at some point we need to talk about trigonometry, don't we? Trigonometry is going to take up easily 6 or 7 questions out of the 25 in the SMO Senior. 1 or 2 of them may be geometry questions that you use trigonometry using the sine rule or cosine rule, but I think those are not the most scary ones. The most scary ones are just things where you have got a whole glut of sines and cosines and you don't know what to do. So I want to bring this to a level that we are a lot more comfortable with. I'm not going to say that you don't need to know the identities, but I want to liken it to taking the MRT. Right? For our non-Singaporean friends, that's our subway. It's like taking the subway. Whenever you're given a trigonometry problem, you're basically trying to get from the starting point to the destination. So you need to know where is your starting point, where is your destination, and you need to know what lines connect them. And the MRT lines are your identities. And the stations are the expressions themselves. You want to be able to travel between them, you need to know how the lines work. And you also need to know the interchanges, the places where there are lots of lines, i.e. lots of identities that are relevant. The first one is to introduce you to, or rather to point out, a very simple starting place, which is from sine x and cosine y. You want to recognize that it doesn't matter what they give you. Sine x, cosine x, and tangent x are effectively just all next to each other. They're only one step apart. So my arrows are a bit wrong, but it doesn't matter. They're all interchangeable anyway. My point is that all of these are just going to be one step away if you need it. Now you start looking at the final destination, cosine x plus y, and you know that cosine x plus y looks like this. You do know that cosine x plus y looks like this, don't you? Which means that you need these and these, and you hit that. Now I'm sure that this looks like a fairly non-mathematical kind of solution. What kind of solution is this? And yes, we haven't done the steps, but this is the logic that you need. Right? I'm just going to give you the values. Don't forget the negatives, by the way. The quadrants are important, but here cosine x and sine y will both be positive, so not that much frightening issues here. Just cosine x is 5/13 and sine y is 3/5. That's all from sine squared plus cosine squared is 1, or by drawing your favorite right angled triangle. So sine x is opposite over hypotenuse, and cosine x is adjacent over hypotenuse. So of course you can calculate the value. Once you know that sine x, sine y, cosine y are just interchangeable, let's look at some more complicated transitions. Here you've got sine 2x, and you want to get to sine to the 6x plus cosine to the 6x. So how do we do that? Well, there are various options. I gave the analogy to taking the MRT because there are some times where there's only one efficient way to go. If they're on the same line, for instance, you tend to just want to go straight there. But sometimes you need to change and get off, and where you want to change and get off, it's up to you. Is your priority to get there faster, or is your priority a bit more comfort? Let me show you, in this case, what I mean. So I'm going to sort of draw this like a map. Now, from sine 2x, one option is to use the identity itself and get sine x cosine x. The other option is, remember that whenever you have sine of an angle, cosine and tangent are always just available to you. To figure out which way we want to go from, we can also start off from the other end. How would I find sine to the 6x plus cosine to the 6x? Well, one way is if I do find sine and cosine. If I knew what sine and cosine are, then of course that would be good. Another way is that if I use my identity from algebra, this is a sum of cubes. Right? Sine squared x plus cosine squared x. Sine to the 4x minus sine squared cosine squared plus cosine to the 4x. This is your factorization, which of course sine squared plus cosine squared is 1. So you can also try to find this. Now, if you want to find the one on top, you realize that, okay, sine squared cosine squared comes from here. And sine to the 4x, cosine to the 4x, you can get that by squaring sine squared plus cosine squared and adjusting. So one way to do it is to combine and use sine squared plus cosine squared is 1 into here. To be precise, what we want would be equal to sine squared plus cosine squared x whole thing squared minus 3 times of the sine squared x cosine squared x. So this is one way you can get there. It is, however, not the only way you can get there, because remember we had the other path, the cosine 2x path. Now, cosine 2x has got a few different representations. One is the 2 cosine squared x minus 1, and the other is 1 minus 2 sine squared x. And so, from 1 minus 2 sine squared x and 2 cosine squared x minus 1, we could also get this. And maybe we don't even need to get sine x and cosine x. We can just work straight from sine squared x and cosine squared x. Now what I've done by drawing arrows here is each arrow is what I consider a one-step, whether it's one-step calculation or one-step identity. So for instance, if you have got 7 over 9 here, then of course this is also 7 over 9, and so you can just compute straight away. But you can also, let's say, compute cosine 2x as 1 minus sine squared x square root that. And then after that, use it to find sine squared x and cosine squared x. My point is that there is no right path. There are multiple paths and you just want to pick the one that comes to mind. So in Singapore, if you are taking the MRT, you would like to find the fastest one. But if you were going to, let's say, a foreign country, you're just happy to get to your destination, right? I don't think you're too worried about getting to the destination in the quickest way. So treat trigonometry something like that. It's a bit like a foreign country to many of you, and that's okay. Now, I want to also just add one more example, because sometimes you have got numerical situations which are a bit more difficult to deal with than the algebraic situations, because you need to figure out which numerical expressions are related and which ones are not related. But just like what we have seen for the algebra, you kind of want to do some associations together. You want to associate things that you believe are going to work nicely, and then from there, hopefully things will go well. So you want to look for the two most closely associated things in whatever it is that you have. And here, I would say that these two are the most closely related because in terms of numbers, adding to 180 degrees, your supplementary angles, adding to 360 degrees, adding to 90 degrees, those are the most closely related numerical values when dealing with trigonometry. So cosine 70 plus cosine 110. Cosine 110 is just negative cosine 70 degrees. And so that is effectively got. Now I want to also take this opportunity to deal with the rest of it, because the rest of it is using our very dreaded sum to product and product to sum formulas, or just simply factor formulas. I want to make you dread it a bit less, because there's actually nothing scary about it. All you need to understand is that it's sum to product or product to sum. Don't memorize the list of formulas. Look at what you want to do and then just try to turn it out. Now you see that cosine 10 degrees plus cosine 50 degrees. So what you would like is to have cosine something plus cosine something equals to something times something. Now I'm leaving it as blanks because let's pretend you really don't remember at all. How do I get my sum to product identity if I don't remember the sum to product identity? You just need to understand that the sum to product identity comes from the compound angle formulas, and there's only one compound angle formula for sine and one for cosine. For cosine, let's say, it will be x plus minus y. You can count it as 2. I like to count it as 1. For cosine, it's minus plus sine x sine y. So cosine plus cosine comes from adding together the two cases. And by adding the two cases, the second one cancels out because of the minus plus. So there you go. This is your sum to product identity. And in order to use it, you have to ensure simply that 10 and 50 are x plus y and x minus y. So 10 and 50 should be the sum and difference. It's pretty obvious that it would be 30 plus 20 and 30 minus 20. Hey, that's convenient, isn't it? I know I'm forgetting all the degree signs, I'm just a little bit lazy here. But one final point before we move on from trigonometry. Please remember your special values. It's like taking the MRT. If you don't bring your EasyLink card or something equivalent to an EasyLink card, you can't take the MRT. It's no point knowing how to get from point A to point B if you don't have anything to get into the MRT. Special angles, please make sure you know them. If you don't remember them, go back to the right angled triangle and derive it yourself. For instance, how do I get cosine 30 degrees? For the 30, 60, 90 triangle, reflect it to form an equilateral triangle. 30, 60, 90 is half of an equilateral triangle. 45, 45, 90 is half of a square. So there is no trigonometry needed to recover the information. Half of an equilateral triangle means that if I write it like this, cosine 30 degrees is square root 3 over 2. So in this case, answer would be 81. So that's just a quick word on trigonometry. And we'll move on to something else which is different looking but has the same idea. Don't remember formulas and theorems blindly. Don't remember trigonometry just as a list of formulas. Don't memorize your binomial theorem as just a very long sum. It is not just a very long sum. The binomial theorem is meant to tell you about how expansion works. The binomial theorem does two things. First of all, it tells you what terms appear, and the second thing it tells you is how many. And it only tells you for the very specific case where you are doing something that is, well, binomial, just x plus y or x plus 1 over x or square root x minus 1 over x squared or something like that. If we understand the reasoning, we can go further than just a binomial. In fact, there's such thing as a multinomial theorem, but let's not go there. We'll stick to trying to understand things a little bit better. When you read this question, it says how many distinct terms are there? Now, you must first understand what is a term. Now, a term is just x to the power of something and y to the something. And like terms means that they have the same powers. We don't really care about the coefficients right now. How many there are is not the concern. The concern is just what are the powers. If you look at x squared plus y squared to the power of 11, you notice that this is going to be degree 22 throughout. Now, degree just means the sum of the powers for each term. So 11 times 2 is 22. For the second one, the degree is 99. 9 times 11. And so in total, the whole expression, 22 plus 99, all of them are going to be 22 plus 99, which is degree 121. Now that means that if, let's say, x is to the power of 21, I know that y must be to the power of 100 because all of them look like that. If x is to the power of 40, then y will be to the power of 81. It's just like your binomial theorem, the what terms, you have got x to the n minus 1 y, x to the n minus 2 y squared, and so on, because there are n brackets, and if you took something from each bracket, you have n things. N things multiplied together means your powers should sum to n. So same logic here. To count how many, since the total is fixed, I only need to count how many different possibilities there are for x. So the first bracket will give you x has 22, 20, 18, 16, all of the things down to x to the 0, which is 1. The second bracket gives you all of these multiples of 11 all the way down to 1. And effectively, you just need to answer what combinations can you get. How many combinations can you get? And the answer is you can get almost anything as a combination. Right? So 1 times this, you get 1, x to the 11 until x to the 99, x squared, then x to the 4, and so on, all the way until x to the 20 would go 31, 42, up to 119. X to the 22, I don't really need that because it has almost everything. Excuse me. It's almost everything except for 22 plus 88 and 22 plus 99. Right, so obviously those are not in this list, but for everything else, they're just going to be alternating between odd and even powers, and quite clearly they don't overlap. I'll leave you to count this because I want to count something else. Here we've counted how many different types of terms, but the other type of question is counting how many of each type of term are there, which we didn't care about in the previous question. So we had the question of what terms are there. Now the other question is on how many. For the binomial theorem, if let's say that you have the x to the r, y to the n minus r term, we often just happily put down it is n choose r. Do we actually know why that's the case? What r things are we choosing out of n? Well, this means that you choose to pick x from the x plus y r out of n times. Right? There are n brackets, and to get x to the r, y to the n minus r, expansion just means pick one from each bracket and multiply them together. Right? If let's say you have a plus 2b, 3c plus 4d, it means this, 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 and this, right? Pick one thing from each bracket and multiply them together. So here, you're picking one thing from each bracket, and you want to have x to the r, means you need to have chosen it r times. Is that not n choose r? So this is actually where you get to do a bit of counting. The SMO has lots of algebra, but a bit of counting is going to show up in questions like this. So what you need to do is just to see how many ways are there to get x to the power of 6 from 7 brackets containing these. Now I'm going to just draw a table of all the different combinations that would work. To get to 6, I can use 3 of the x squared. If I use 3 of the x squared, means I cannot use any x. If I use 2 of the x squared, that gives me 4 x's, and I need 2 more, and the total is always 7. So the rest will be 1s. 1s are basically fillers. If I use 1x squared, I need 4 more, so 4 more is 4 more. And finally, if I don't use any of the x squared, then all the 6 x's come from 6 x's. Now, you need to count how many ways this happens. So the corresponding term, out of 7 brackets, you picked 4 of them to be 1 and 3 of them to be the 2x squared. So 7 choose 4, and then 1 to the 4, I don't need to write that down, 2x squared cubed. That's going to be that term. You see how this echoes your binomial theorem? It's not just a theorem, it's basically just reasoning how many times each thing is picked. For this one, you pick 3 ones out of 7, and out of the remaining 4, you pick 2 x's. Same for the others. And I'll leave you to actually do the counting. The counting is not so important. The more important thing is how exactly do we form the term that we want. Once you understand that, you can even deal with 4 terms, which I don't actually know if there's such a thing as a quadrinomial. I have no clue, but it doesn't affect our solution. You basically just take x cubed as 4x cubed bunch of 1s, x squared and x with smaller bunch of 1s, or 3 sets of 2x with even slightly smaller bunch of 1s, and then you count how many times each of these appears. The first one appears just 8 choose 1. Second one, 8 choose 1 and 7 choose 1. And the third one, 8 choose 3. Once again, calculation will be left to you. But just like trigonometry, it's more important to understand what's going on than to just know the theorem. Now, just knowing the theorem is going to help you easily to get, for example, an honorable mention or a bronze. If you just work very hard and learn your theorems, there is no question that you can at least get a bronze just by, let's say, knowing your quadratics, knowing your trigonometry, knowing your logarithms, knowing your binomial theorem. But you are kind of hard-capped there, and you're going to be feeling that there's this mysterious sense of why exactly am I unable to solve questions that other people in my school or in Singapore seem to be able to solve. That's because you need to understand what's going on behind the scenes. One final point which I want to add is on this very often ignored word in the question, which is the word integer. You see algebra and you just get to work. And you don't pay attention when the question suddenly changes from real number to integer. As I mentioned in the junior video, integers are limited. Integers can be listed. If I told you that I've picked a positive integer less than 5, you can list out 1, 2, 3, 4. If I told you I've picked a real number less than 5, good luck listing out real numbers up to 5. It's uncountably many. That means that a very common approach for these questions on integers is to try to make a finite list appear, and either you just check them, or if they all work, then you just pick whatever the question asks. If it's smallest, give smallest. If it's largest, give largest. If it's total, then add them all up. So for instance here, do not start guessing what n is. Don't guess that, okay, is n equals to 1? No, that doesn't work. Is n equals to 2? No, don't do that. What you should do is just good old-fashioned long division. And this is quite possibly the shortest long division you've ever seen in your life. It is 2021. That's the end of your long division. really, that is the end of your long division. So what do we do here? If we want this to be an integer, it means that 2021 squared over 2021 plus n must be an integer. And that implies that 2021 plus n is a factor of 2021 squared. Remember, I commented on the original video that you should know the factorization of the year. If you took the SMO Senior 2 years ago, or if you took the SMO Junior 2 years ago, as many of you did, I hope you remember still that 2021 is not prime. It is 43 times 47. And so therefore, if you want to get something a little bit bigger than 2021, because this here is more than 2021, the smallest thing you could get is 47 squared, right? 43 times 47 is 2021, so 47 squared would be a little bit bigger. Okay. And I'll leave the calculation to you for what n is. You have to also be able to handle small twists in the story. Small twist in the story, meaning that what happens if what I just did looks a bit different? So let's say you just tried to do the same thing and say, okay, wait, I can't just put 20 over 3, right? That doesn't work. Oh dear. Oh, what do I do now? Well, the answer to that question is don't do that. Understand the principle of long division is to get a remainder and you can work from there. So for instance, I can actually just take a twist on my long division where I take the largest integer that fits and so I write this as 6 plus 2n plus 2056 over 3n minus 6. Okay, and so now this has to be an integer. How does this become an integer? And what is the largest positive integer n where that happens? Well, the largest positive integer that happens, as n is very big, eventually the bottom will exceed the top. And in fact, we can just say that it is going to be such that 3n minus 6 catches up to 2n plus 2056 and eventually surpasses it. And so the largest would be the point when they are equal. The point when they are equal is the last time where it would actually meet. So this must be the place, because after that, they're never going to meet again. It's going to be stranded between 0 and 1 because the bottom is going to increase by 3, the top only increases by 2. Some of you don't like having to deal with this. You might say, well, how come this is different from the last one? If you're thinking that, then quite honestly, you have kind of missed the point of doing Olympiads, right? The point of Olympiads is not that everyone should have taught you everything before you do the competition. As someone who sets questions once in a while, I'm trying to set questions specifically to test things that I have not taught my students or have not explained in any of my videos. That's always the objective. So if you are going into an Olympiad, of course you should try the questions that you find familiar. But in the long run, the key thing for Olympiads is often just a healthy dose of common sense. A little bit of reasoning. These don't fall into any topic, it's just common sense. For instance here, if you're asked to find the maximum value of fx. If you've learned a bit of calculus, feel free to try to do some differentiation. But if you have not learned calculus, how do you find the maximum value of this? One simple way to go about things is just try x equals to -2 and 2. Try the extreme values, and 90% of the time, one of them is going to work. And let me explain to you why that is actually true here. Now that's true here because if we use the same quote-unquote long division that we did earlier, it will simplify to this. Now 2x plus 5, this is going to be increasing as x increases. 5 over x plus 3 is decreasing as x increases. In other words, you are taking a bigger and bigger minus smaller and smaller, so overall it is of course increasing. Now if it's increasing overall, do you want to pick x is -2 or x equals to 2? We actually don't know because you're squaring it. So if you're squaring it, the extreme values are the places you need to check, because let's say if the extremes are -8 squared versus 2 squared, you prefer this one, so we should check. But if you check it, x minus equals to -2 in this case is not the extreme value you want. 2 is actually the one that you want. So reasoning. Sometimes you just need to use reasoning like, it's getting bigger, it's getting smaller. There's no theorem for that. Bigger means bigger, smaller means smaller. And to end off, you get your one and only appearance of a non-algebraic question. That's how the SMO Senior is going to be, by the way. It's a lot of algebra. But the ones at the tail end, usually at the back, are not always the hardest questions. They're just the not algebra questions, such as this one. You're asked for the digit sum of the digit sum of the digit sum of 2020 to the power of 2021. And this is a classic question, but if you've not seen it before, it's still common sense. Anytime when you're doing something that is not in a topic that you have learned, but sounds vaguely familiar, ask yourself, why does it sound familiar? And there's a 50% chance that it is exactly what you should be doing. Digit sum, I believe you know that this is your divisibility test for 9. So when you take a digit sum, let's say 9, 8, 7 and 24, 24 divided by 9 is 6, meaning that the remainder when 987 is divided by 24 is, divided by 9 is also 6. That means that in this case, if you want to find out what is a digit sum of b, to use a touch of modular arithmetic notation, it means that all of these are going to be the same modulo 9. And the reason why this is useful is because it is going to shrink very fast when you take a digit sum. If let's say you took 1,000 nines, that's a very big number. After you take the digit sum, you get 9,000. That's not such a big number. So things drop off very, very fast, no matter how big a number that you start from. So to use a very crude estimate, 2020 to the power of 2021 is less than 10,000 to the power of 2021, which is 10 to the power of 8,084. So it has less than 8,084 digits. Terrible estimate, I know, but I'm just trying to get the point across. Because immediately it means that A is less than 80849, which is going to be less than 100,000. Very rough estimate. If B is the sum of digits of A, that means that it's at most 5 digits. So B is at most 5 nines, which is 45. And so the answer is going to be really tiny, but I need to know what is it modulo 9? What's the remainder when 2020 to the power of 2021 is divided by 9? So yes, let's use a little bit of modulo arithmetic. First of all, 2020 divided by 9 remainder is 4, just 2 plus 2. And then after that, your pattern for powers of 4, modulo 9, it goes 4, 16 gives you 7, 7 times 4 is 28, that's 1, and so the repetition is very fast. And 2021 divided by 3 gives you a remainder 2 here, which is 7. And so therefore, your answer is going to be 7 modulo 9 and less than 45. Hopefully you realize that the digit sum of B is very limited. Right? Your answer, when you take the digit sum of 45, is at most 12. And so a number that's at most 12 and 7 mod 9 is indeed going to be 7. Would we consider this to be common sense? Maybe this is uncommon sense. It's not the most obvious thing. But what I mean by common sense is that when you're trying to break through harder questions, use your past Olympiad experience. If that's 1 month, 1 year, or 5 years, use that. A lot of times, questions are meant to be callbacks to old ideas you've heard long ago in primary school or in SMO Junior. So they just look a bit more scary now, but they are the same thing. So at the end of all this, to summarize, for the SMO Senior, what should you be doing? Firstly, make sure that you're comfortable with the basic identities. Trigo, logarithms, you need to know a little bit. You can't know nothing. Also, don't be afraid of algebra. You need to know what's good and what's bad. So quadratics are good. Logarithms, not scary. Polynomials, look at the roots. Take the big ideas away from what we have discussed and not the numbers, the algebraic solutions, and the expansions. Don't worry about that because it's not going to be asked again. I can assure you that none of the questions that we have covered here will be asked exactly, but the ideas, if you look carefully at all the past SMO Seniors, are all extremely relevant. So I hope some of this helps. If you have any comments, please leave them below. And if there are any of the questions which you would like a little bit of further explanation on, leave a comment as well. I'm sure someone, myself or someone else, will be happy to help you. So all the best to you and hope to hear from you soon.